All right, welcome everyone. So today, diving back into t-testing, but moving away from the two independent samples t-test that we've been doing so far. It's going to be a little bit different. Before we get into that though, the question today is this one, and it's going to take a bit of thinking. So the question is, which three things of those in the purple boxes affect the size of the test statistic and hence the p-value? So what I want you to do here is not just think about the answer to the question, but look at all those terms in the purple boxes and check to make sure that you understand what each of them are. If you do, that's great. Then you can start to think about whether or not that particular thing is going to have an impact on the size of the test statistic. Okay, so pause here and have a good think. And when you're ready, you can restart the video. All right, so instead of jumping straight into the answer, let's have a look at a couple of things first. So I want you to think about how the test statistic and the p-value link together. If we have a small test statistic, we place our test statistic, in the case of a t-test, our t0 test statistic, we place it on the t-distribution. If it's not very big, then we're going to have quite a large p-value because the p-value comes from that tail proportion and we're not pushing far enough out into the tails. And for a two-sided, you go both ways and you get a big p-value. So small test statistic, big p-value. And so the reverse is true as well. If we get a big test statistic, then we're pushing out into the tails where things are unusual. And remember, our t-distribution here is a stand-in for a distribution of test statistics we would expect to get if the null is true. So our t-distribution is null world when the null hypothesis is true. And it's a distribution of the test statistics we would expect. So if we're pushing right out into the tails where things are unusual, that means our test statistic is unusual if the null hypothesis is true. Okay, so big test statistic, itty bitty p-value. So that's the connection. So how do we get a big test statistic? So let's have a look. So if we have a look at our formula for the test statistic, if we change any of the things in the formula, that's going to change our test statistic. So let's have a little look. So we've got our estimate and our hypothesized value. Now for the tests we've been doing so far that have alternative hypotheses that look like this, our hypothesized value is 0. So far we've not seen a hypothesized value that's not 0, but watch out, we will see one. But so far it's always been 0. But the key thing in that top row is the size of the difference between the estimate and the hypothesized value. The hypothesized value is what you expect the parameter to be if the null is true. And the estimate is your estimate for the parameter based on your data. So if what you're seeing in your data is different to what you expect if the null is true, then that's going to make your test statistic bigger. And that's probably the most important thing, or the most impactful thing. And remember, our general definition for a test statistic is that it's the measure of the discrepancy between what we expect if the null was true and what we're actually observing. So that top part is really that in a nutshell. The bottom bit, the standard error, so for a test statistic, we take that difference and we calculate it in terms of standard errors, that we've got what we call like a standardized measure, and that's so that we can put it on a t-distribution which is standardized in terms of standard errors as well. So here's our formula for standard error for a mean. On the top we've got the standard deviation of the data, that's the variability, and underneath we've got the sample size. So those three things in sort of the purple speech bubbles there, those are the three things that are going to affect the size of our test statistic. So I think this one's fairly straightforward. If there's a bigger difference between the estimate and the hypothesized value, our test statistic goes up. If there's a smaller difference, our test statistic goes down. Standard error is a little trickier. So for variability, if our variability goes up, and remember, we'll just write this here. X bar would be here. So if our variability goes up, then this is going up. So the standard error goes up. So our test statistic goes down. So more variability, smaller test statistic. Remember, more variability, that's like more uncertainty, right? A less clear picture of what's going on. And if you're more uncertain, then being able to get evidence against your null hypothesis is going to be more difficult because you're not really sure what's going on. Sample size. So if sample size goes up, then the number at the bottom of this fraction goes up, the standard error goes down. That's the number at the bottom of that fraction, so the test statistic goes up. The more data, more better. More data, you've got a clearer picture of what's happening. So you're going to have sort of more confidence when it comes to having evidence against your null hypothesis. But it always comes down to this bit here. That bit has to be big before we can, before we're going to get a big enough test statistic. The variability in the sample size is just kind of helping us out a little bit. It might be interesting to note as well, standard error for a proportion, you can't get standard deviation for categorical data, it's only for numeric data. The standard error for a proportion is only related to the sample size. So you can't really talk about variability of proportional data. It's kind of like saying which has more variability. Yes, 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 no, or yes, yes, no, no. Like, it's not a measurable thing. So for categorical data, when we're looking at the standard error of p hat of a proportional estimate, then we wouldn't talk about variability. We'd only talk about sample size and the distance or the difference between the estimate and the hypothesized value. Another way that sample size comes into play is that sample size has an impact on the degrees of freedom. So again, not for proportions, because when you do proportions, the degrees of freedom is always infinity. But let's have a look how sample size is going to come into play here. So let's say our test statistic was 2. Okay, so it's going to go in right there. We'll just zoom in. So if we had degrees of freedom infinity, then this is the size of our p-value. Right, my beautiful colouring in there. So it's quite small. If our degrees of freedom was much, much smaller, so our sample size was smaller, our p-value, instead of just going up to the green line, maybe goes all the way up to the yellow line. So now it's bigger, right? Our p-value is now a bigger area. So as degrees of freedom decreases, our p-value is going to increase. And that's the same impact that sample size was having before. So it doesn't impact on the test statistic, but it does impact on the p-value. Okay, so there's kind of a lot going in there. So I've put on this slide the recipe for a big test statistic. So I've written it in terms of trying to get T0 as big as possible. We want a big difference between what we observe and what we expect under the null. We want a small standard error, which means a small amount of variability or a small standard deviation, and we want a big sample size. Okay. So you can see going through this checklist of what we need to know in Chapter 8, we're doing pretty well so far. We've covered a lot of them. What we haven't really talked about is number 3, selecting which test to use. And that's because we've kind of always been using a 2 independent sample t-test. Let's have a look at where that might not be the most appropriate test. So cast your mind back to the kiwi fruit example. That was a 2 independent sample t-test because we randomly allocated to groups. One group ate the green kiwi fruit and one group ate the gold kiwi fruit. But how else could we have done this experiment? So let's have a think. What if you've got some people that really, really hate kiwi fruit? They just hate it. It doesn't matter whether you randomly allocate them to the green group or the gold group, they're going to give a really low rating. Like maybe this person here is just a full-on kiwi fruit hater. Alternatively, you might have someone who's like a kiwi fruit lover and they totally love kiwi fruit. You put them in the green group, they're going to love it. Put them in the gold group, they're going to love it. But you don't really care about that. You don't actually care how much they like the kiwi fruit. What you do care about is whether one kiwi fruit is liked more than another. So what if instead of having each person only eat one type of kiwi fruit, what if you had each person eat both, give a rating, and then look at how different they were? So let's say this was one person. They ate the green one, they gave it a 3. They ate the gold one, they gave it a 1. There's a difference in the liking scores there if we go green minus gold of 2. Let's say this was one person, we've got a difference of 1. This is one person, no difference. This person, a difference of -1 because we're still going green minus gold and they like gold more. So if we did that, we'd end up, instead of 2 separate dot plots, we'd want to keep the connection between the pairs together, and we'd get a dot plot of the differences. Now, what's the point of this? How is this better? Well, it means you're taking away sort of kiwi fruit hater effect or the kiwi fruit lover effect, and you're just looking at how much, like whether one is better than the other, which is all you really care about in the first place. And when we think about experiments, we want to minimize the impact of confounding factors, confounding variables. And that's what this is doing. So any other factor that's coming into play here about the particular person and their taste preferences, this difference here, just for that one person, so their green score and their gold score aren't different for any reason other than that person likes the gold kiwi fruit more, which is what you're really getting at. So it's about balancing confounding factors. So have a look at these 6 examples of possible studies and think about which would be best investigated using a paired design. So a couple of things to think about. Firstly, you want to think, like, could it possibly be done as a paired design? Could you have, I think these are all about people. So could you have one person exposed to both treatment levels? And sometimes that's not possible. So that's the first thing. Can you possibly do it? And then think about what it would achieve. So the reason you would do a paired design, the reason that would be better, is if there's more variability between individuals than between the treatment levels. So if there's a bigger difference between how much people like kiwi fruit than there is between how much people, the difference between green and gold kiwi fruit, then a paired design is better because you get rid of all those individual differences between people and you just look at, for each person, the difference between the treatment levels. So have a bit of a think, pause the video, write down which ones you think would be best investigated using paired data, and when you click play again, we'll go through what I think. All right, so let's have a look. So I think one of the first things to think about is, can we even run this as an experiment? And you can do paired data for observational studies, but it is much less common. So let's think, do surfers or skateboarders eat more? Well, we're really looking at people who are surfers and people who are skateboarders, and they're two different people. So this sounds like we're comparing across two independent groups of people. Number two, we've seen this one already. So do Nike Vaporfly shoes make you run faster? Now, for this one, you could randomly allocate one group of people to run in the Nikes and one group of people to run in other trainers, and you could look at how fast they run. But there are quite big differences between individuals there. So between how fast I can run and how fast you can run, there's a big difference already. And if one of us, like if you're a much faster runner, if you end up in the Nikes, it's going to look like the Nikes make you run faster, but it's actually just you are faster. So this one, it might be better if you make me run in one pair of trainers and then you make me run again in the Nikes. You need to give me a break in between so I can recover. And you might even want to randomly allocate whether I run in the Nikes first or in the other shoes first, so that you're, again, minimizing any impact of confounding variables like the time of day or muscle strain from the previous run or whatever it is. So this one would be really good to do as a paired experiment. Okay, and again, it's because you're getting rid of the individual differences between people. Okay, number three, which sport makes you more hungry, surfing or skateboarding? So it sounds a lot like the first question, but it's phrased a little differently, and that changes it a lot. So it's written a lot more like an experiment question. Which sport makes you more hungry? So we're looking for like a causal link here. And we're not talking about people who already are surfers or already are skateboarders. We're talking about the sport itself. So you could randomly allocate to two groups, make one group go out surfing, one group go out skateboarding, and then put them in front of a buffet and see who eats more. But again, there are quite big individual differences between people and how much they eat. So it might be better to have randomly allocate everyone to go surfing or skateboarding one day, and then the next day randomly allocate them or put them in the other, send them out for the other sport, and then compare for each person as a paired design, each person which sport had them eating more, or the difference between how much they ate after each sport. Okay, number four, do you perform better on a trivia quiz working with a group or working alone? So this one's quite a difficult one because you're the individual, and we'd be looking at your score. But if you're in a group, you'd be looking at the whole group score, and you'd want to be doing the same quiz so that you had a fair comparison. And you can't have someone do a quiz individually and then do it again in a group if it's the same quiz, because I know the answers to the questions. So it might be quite difficult to do this one as a paired design. It wouldn't necessarily be impossible if you had similarly difficult trivia quizzes that you could maybe do as a group or alone, so you could do it under both treatments. But it would be a very difficult one to do that way. Would be possible, but quite difficult. And in general, I think it's just a very difficult one to think about because your units, your response variable is the score on the trivia quiz, but who are your units? Is it just the individual, or is it the group score, or is it? It's tricky. So I put that one in there just to really get you thinking about design, and you could probably have answered that one either way. Number five, do elderly people report less loneliness when they have a pet? So to do this paired, you'd have to have an elderly person, have them with a pet, and have them without a pet. And that's going to be quite challenging, because if you put them with the pet first and then take the pet away, maybe they'll be more lonely when you take it away because they miss the pet that they had the previous week or whatever. If you do it the other way around, it's different. So you've got this issue of a time effect, or the previous treatment is going to impact on the other one. So you can't randomize the order. You'd only have to have like a before and an after. So you could do it that way. It also might work to do it as two independent groups. And in terms of level of loneliness, are we expecting huge differences between individual elderly people and how much loneliness they're reporting? I don't know. I mean, people are different, so maybe they would. But potentially with your random allocation, you might be able to balance it out enough. So again, that one you could do either. Probably two groups is going to be the easiest way to go, because otherwise you wouldn't be able to put that random ordering of the treatments in. You'd have to do a before and an after, which does mean you haven't quite minimized some of those confounding effects. Is performance on a memory test improved after learning a memory technique? Now, in terms of individual differences between people's performance on memory tests, there'd be quite big individual differences. If we're looking specifically at after learning a memory technique, you probably would want this as a paired design. But similar to the number 5, we'd have to do a before and an after. We couldn't randomly allocate, but probably paired would be better here, because you're looking at their performance on the test before they've learnt the technique compared to their performance after learning the technique. That word after is kind of giving it away. Again, you could do it as two groups. You could randomly allocate one group to just do the test. Another group, you could teach them a memory technique and then get them to do the test. And you could do it that way. I think you could probably argue either way for this one as well. But I'm going to put down paired. So you can see this isn't sort of a clear-cut issue. In terms of study design, when the researchers go to do their study, they think a lot about these things, about minimizing the effect of confounding factors, and they'll try and design it as best as they can within the constraints, but it's not always perfect. So here's another example, and this one is a bit more clear-cut. So our top example, the researchers are investigating the time it takes to answer call center queries, and they're comparing Team A and Team B. In the second example, they're looking at different stores and their sales, and they're looking at comparing before a sales marketing campaign and after the marketing campaign. So which of these two would you put as paired, and which would you put as two independent samples? So pause the video, have a think, and once you're ready, we'll move on. Okay, so for the top one, for Team A and Team B are totally independent. There's no connection between this person and this person. They're two totally different people. So these are two independent groups. So for how we set out the data, what we want is we want a rectangular data set. And a rectangular data set, if you go back to chapter 1, means that each row is one entity. So an entity or a unit for the call center question one unit would be one person, one team member. So for each team member, you need to know what team they're in and the time it takes them to answer the call center queries. And that would be one row. Right, so this is your one. Oh, my pen stopped working. Yep. There we go. So your one entity or your one unit is your one row. So if we're doing two independent groups, which we should for that one, then our data would look like this. For the second example, before and after a marketing campaign, right, there is a link or a connection between those two values. They both come from the same store. So the before sales and the after sales are not independent. This before sale and this after sale, not only are they not independent, they're really linked. They're both from the same store. So for this one, we would want to do paired data. So we'd actually want like a third calculation here, which is the difference. And we'll go before. Well, we're expecting after to be higher. So we'd maybe go after minus before, which in this case, -1. Right, but for each one you'd calculate the difference because that's what you're really interested in. How has it changed since the marketing campaign? Now for this one, you're probably already guessing, but we want the data set up the other way, and we do. So in this case, each unit is a store. So for each store, we want one row. So when it comes to figuring out how your data should look, it's important to remember one unit, one row. And this is for a rectangular data set. And rectangular data sets are sort of, that's the layout that we need for most statistical software, and definitely for everything we use in this course. So for Insight, for SPSS, you need a rectangular data set. One unit is one row. When you come to do assignment 3, you will have to choose which data to use. So you will have a question and you will have the data in both formats, and you'll need to pick which one is most appropriate for that study. So the first thing to decide is it paired data or is it two independent group data? If it's two independent groups, it looks like this. If it's paired, it looks like that. Okay, and often it's quite a difficult decision to make, but you're looking for a connection between the two sort of categories, or between the two treatments. So here they're connected because they're both from one store, and here they're not connected, they're two completely separate people. I've just put in here as well, so if you are taking that sort of paired data format into Insight and you want to produce a dot plot of the differences, which would be really useful when you're looking at paired data, you might have to calculate that extra column and put it in your Excel spreadsheet. You can also manipulate variables in Insight and create one that is the difference between them. It depends what you're more comfortable with, but you can have a play around with both. But to actually produce a plot of the differences, which is what you'd want, you wouldn't want a plot of the before and a plot of the after because they're not independent. You'd want just a plot of the differences. You'd have to calculate the differences and put it into the data file. Okay. So here's a bit of a summary. So in the box on the left, paired data retains a connection between the two measurements for one individual or one unit. Okay, and this is useful to prevent bias where individuals are likely to differ in their baseline levels. So some people are just better runners than others. Some stores might just have better sales than other stores. So there's lots of differences between individual units. You've minimized the effect of that, or you've reduced the impact of that confounding variable. So each row, one entity, one unit, one person. Okay. So let's have a look at an example of a paired data design. So this example here on page 6 in your book, researchers are interested in determining if a pre-run drink of cold water has a different effect on run to exhaustion times compared to a pre-run ice slurry. So this sounds like kind of a weird study, but there is some theories around how your body works, and that part of the reason why you become exhausted when you're exercising is that your body is overheating. So if you can keep your body temperature down, it's going to take you longer before you become exhausted. You're going to be able to run for a longer time. So that's what they're investigating here. If maybe this ice slurry can cool your initial body temperature and give you longer before you overheat. So for the design, they only had 10 volunteers, all male, healthy, moderately active. And there were 2 trials. So 5 of the subjects were randomly assigned to have the ice slurry, and the other 5 the cold water. And then in the second trial, it switched over. So every single volunteer did both treatments, and you can see that in the data table below. But half of them did the ice slurry first and half of them did the cold water first. And for each trial, the time taken to run to exhaustion was recorded, and these are all in minutes. So what we're interested in here, if we have a look, we can see, we look at person number 10. This person's a pretty good runner. They can run for over an hour with the ice slurry or nearly 50 minutes with the cold water. So they're a really good runner. Compare that to person number 1, and they're barely getting up to 40 minutes. So there's a lot of individual differences between the units in terms of how long they can run for. But we don't really care about that. What we care about is the difference between how long they can run with the ice slurry and how long they can run with the cold water. So we calculate the difference, and our difference here is ice minus water. Okay, so for all of our differences there, they're all positive, meaning every single volunteer in our experiment ran for longer with the ice slurry than with the water. Okay, so let's look at our study design. So we do not have 2 independent groups or samples. Our ice slurry group and our water group are the same people. So they are related, and they're paired by each person. So our units are the individuals, the volunteers. The treatment is the drink type, and the response is how long it took them to run to exhaustion. And specifically our response here that we're really interested in is just the difference in run to exhaustion times for the ice slurry and the cold water. So we've just got one response variable, one thing that we really care about, which is the difference. Okay, and this is what the plot of the data looks like. Now there's only 10 data points here, so it's a bit tricky to really talk a lot about the shape and the spread, but we'll do what we can. So we can talk about center. So it looks like we've got an average somewhere around about 9, and all of our differences are positive. We could maybe indicate like a slight negative skew. Oh, why? That's weird. Yeah, maybe a slight negative skew. Again, tricky to tell with only 10 data points. Spread, we could just say that the differences go from around about 2 to about 14 minutes. There's nothing else really interesting there. So it's quite difficult to describe data when there's only 10 points, but we do what we can. For our hypotheses, our null hypothesis same as before, it's our like, there's nothing going on, right? Really boring. So there's no drink effect. And that would mean there'd be no change in, or no difference in the run to exhaustion times for the two different drinks. So the underlying mean of the differences, because we're only looking at the differences, is 0 in that situation. So our parameter here, mu diff, here we go, I have defined it. So where diff is ice slurry minus cold water, the mu diff is the underlying mean difference in the run to exhaustion time. Our alternative, we've gone two-sided here, so just that it's not 0. Is there an argument for a one-sided hypothesis here that it could just go greater than 0? Oh, yes, there probably is. Like I said, there is some research that says that cooling your body temperature will help you to be able to run for longer. But we already looked at the data and that's what we saw, and we don't want to do data snooping. And our default position is always a two-sided hypothesis. So we're going to be conservative here and go two-sided. Okay, so here's where we're at the moment. We've got our data, and it's from an experiment. So we can't generalize it beyond the 10 people in the study, but hopefully we're going to be able to make a causal claim. And this time we're not looking at, are the two groups looking different, but are these differences, do they look like they're different from 0? And it does look like they are, but we're going to have to continue on with our test. But stop, before we do our test, we need to check some assumptions. Okay, so these were our assumptions for a 2 independent sample t-test. But luckily for us, it's about to get a bit simpler because we don't have a second sample. So we only have to check assumption number 1, independence of observations within the groups. And remember, what's in here are the differences. Okay, so we just have to make sure our differences are independent. That like each person that did the running and got a difference, their difference is independent from anyone else who did the study. So remember, usually we deal with that one by ensuring our study was well designed. Luckily for us, we had random allocation to the treatment. So the order in which they did the 2 treatments was random. So that's going to ensure independence of observations within the sample. Number 3, the populations are normally distributed. So for that one, we look to the data and we can still use the same guide, but we're sitting over here at small now. So we can't have any outliers, and at most we can get away with slight skewness. So let's look back at our data and just check. There's no outliers or clustering. It's super hard to tell with only 10 data points. But I can't see anything that's super freaking me out and making me panic. It's pretty difficult to tell in a sample of 10, but we do what we can. So for this one, I'm going to say that it's okay to use T procedures. Okay, so our assumptions for the paired data t-test are met. Now we need to go and do our paired data t-test. I'm going to show you how we would do that on SPSS. Now, if you are using SPSS from home, there are a couple of different options you have. So I think in my last video, I said you'd want to go through Flex IT. That's one way to go. The other option is that because of the COVID situation, IBM SPSS has actually granted permission for students to download and use a version of SPSS on their home computers with a license that lasts until the 15th of June, so until the end of first semester. So you can go and download SPSS. There are instructions on how to do that with assignment 3. Whatever you're going to use, whether you go for the Flex IT route or you go for downloading it on your computer, there are more than likely going to be technical hiccups as you try to get started. So don't leave it till the last minute. figure it out now, have a play around with the system, download the data from Canvas, like the lecture data sets that we're using today, for example, and have a play around and see if you can get familiar with it. You don't want to leave it till the last minute because, like I said, undoubtedly there will be some technical issues. If you get stuck and run into technical problems, then if you can't figure it out yourself, do use the online stats lab. So on Canvas, under help available, there's information on how to contact the lab tutors. And that's through Google Hangouts while we're remote. So take advantage of that as well. Okay, so assuming you get into SPSS, this is what it looks like. You've got two tabs, the variable view and the data view. So we've got what looks like two numeric variables, but what we know is that they're paired. So we kind of need this third column here, which is the differences, but SPSS calculates that for us when we go into our analysis. So we're comparing means, paired samples t-test, so fairly logical so far. We need to get our subtraction right, so it's going to go variable 1 minus variable 2. And I think, yeah, that's all we needed. There we go. So we've got our data up here about the two groups. We basically just ignore this. This one is a little bit more interesting because we've got our sample size, but again, we're not doing correlation. We're doing a paired samples t-test. So this is the good one. So here's the mean. This is our estimate. This is X bar. Standard deviation, again, of the differences. And it shows here the order you did the subtraction in. So if you did it wrong, you can just go back, do it again. We've got a 95% confidence interval for the difference, test statistic, degrees of freedom, and p-value. Okay, so let's go look at the p-value. So remember, it's not actually 0, it's just really, 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 really small and looks like 0 when you round it to 3 decimal places. But either way, we have very strong evidence against the null, so our null is up here, that the underlying mean of the difference is 0, or we have very strong evidence for the alternative, that the underlying mean of the difference is not 0. Confidence interval, so I've just rounded it. We don't want to go crazy. All of our data was to 1 decimal place, so that seems like a good rounding to go for. Interpretation, 95% confidence, underlying mean difference in run to exhaustion time, somewhere between 6.9 and 12.1. So it gets a bit easier actually when we jump to paired data because we're starting to talk about just one mean. So interpretations actually get a bit easier. But what does the 6.9, 12.1 minutes mean? It means that on average, 6.9 minutes longer when they drank the ice slurry. So we still have to remember the order in which we did our subtraction so that we can interpret in context. And that's what we're going to do for our conclusion. So our conclusion, remember, just to the 10 people in the experiment, but we're going to be able to say that the difference is caused by the drink type. Okay, we have an experiment because of that random allocation. So for these 10 runners, ice slurry gives a longer run to exhaustion time, right, on average somewhere between 6.9 and 12.1 minutes. We don't have a random sample. The volunteers were healthy, moderately active men. Potentially we could generalize to other healthy, moderately active male volunteers, men, assuming that they were not different from those in the study. Okay, so that takes us to the end of that example. The second example you have for paired data, use the link on Canvas to go to the interactive workbook, and there are videos in there as well. Watch out, there are a few curveballs in that one, but hopefully as you go through, you'll figure it out. Okay, and I will meet you back here for part 6, which is moving into another type of test.